Welcome to
Yes.
welcome to our morning session. And today we have, I believe, a great day. Yeah, because today we have outstanding speakers at our school. And it's my great pleasure today to present the first speaker, Professor Gerardo Adesso from the University of Nottingham in the United Kingdom. And I would like to present you to say a couple of words about Professor Gerardo Adesso. He has graduated with Master Science in Physics from University of Salerno in Italy in 2003. In 2007, he got his PhD with great excellence also from the University of Salerno. And in 2007, 2008, he was working as a postdoc in Barcelona and also at Salerno. Starting from 2009, he was working for the University of Nottingham, first as lecturer, and in 2016, he is a full professor. Starting from 2022, he is research director. And Gerardo has a lot of awards. I just may mention a few. For example, 2017, he was considered as an outstanding supervisor of the year by the version The Times Highest Education. He was finalist of this concourse. In 2021, he was considered by Clarity Analytics as a highly cited researcher in physics. In 2026, 2017, he was considered, he was got World Economic Forum Young Scientist Honor. Yeah. Gerardo has a lot of publications in very high-ranking journals. This is more than 180 journals, or near 200 papers. So if, of them, there are from them 55 in Physical Review Letters and 3 papers in Physical Review X. This is very high-ranking journals in the physics world. Yeah, and speaking about scientific contribution of Professor Adesso, I would like to mention that he's well known as an excellent quantum researcher. I told you yesterday that we will see a lot of things from the first hand of quantum metrology scientists. Professor Adesso is one of the most prominent scientists in researcher and in quantum metrology. So he has contributed demonstrating the operational value of general quantum correlation for metrology. He also considered multi-parameter estimation formula. I believe today he can mention about his very nice results. Also, he is a researcher who working in this border. I yesterday talking to you for border between classical and quantum worlds. You're welcome. Here's one of the border officer, sorry, who is between these two worlds, yeah, who is checking what is quantum, what is classical, one of the most important scientists in this field. And also, he is an author of quantum research theory, what is useful for quantum things and for classical things. And he has made also very interesting contribution in quantum thermodynamics. So I believe today we enjoy a very nice lecture. And please don't hesitate ask Professor Adesso questions, short questions during the lectures, raising hand. Gerardo, I will be your representative here. Locally in the audience, you will see audience, and for online audience, Anton Svetlichny. Just I would ask you to make 2 interruptions, 2 coffee breaks during our lectures, 2 short coffee breaks, maybe 5-10 minutes. And during coffee breaks, maybe you will be able to use this microphone, another microphone, in order to maybe to speak with Professor Adesso, but also give him a chance to take a coffee. Okay, Gerda, you're welcome. Your audience
Okay.
is yours.
Thank you very much, Andriy. I mean, you were too generous with all these comments, but yeah, basically, I'm just someone who likes quantum stuff. And I'm hoping that many of you will actually continue this line of research, which we started, many people before me started a century ago. I'm sure Andriy already mentioned this is the International Year of Quantum, and we still don't understand quantum mechanics. It's been 100 years, we still don't understand it. But the more we try, the better we figure out what we can use it for. And the whole business of quantum metrology and quantum sensing is to recognize which ingredients of quantum mechanics allow us to beat limitations in achieving precision for estimating parameters that we cannot directly measure. So yesterday, I understand you have had some introduction just to the basic formalism of quantum mechanics. It is a lot for you to learn in a few days, right? And then you had something more on the statistical side of estimation theory. The idea is that, yeah, we really want to construct estimators for parameters of interest, and we want them to have the smallest possible variance. So we need to estimate the values of those parameters as precisely as possible. And you can go to a certain level when you just use classical techniques, but it turns out if you really want to know what are the fundamental limits, so what is really the most information that you can extract about a physical parameter, you need to go beyond classical statistics and you need to use quantum techniques. So the whole field of quantum metrology is built around this, the fact that we can exploit features which are generally quantum mechanical, and they can be features in the probe state, say entanglement, coherence, and other resources. Andrew was talking about resources, or they can be just features at the end of the procedure, like enhanced measurements, which do not obey classical statistics. You can use a combination of these to your advantage so that you can push the limits of precision in estimating parameters you care about. Parameters that can be, I don't know, magnetic fields, that maybe you want to estimate to map your brain. They can be temperature of a state. They can be, so you can monitor the surface of the earth and predict wildfires. And it can be, I don't know, variations in the gravitational field so that you can detect whether there's, I don't know, some hidden holes and structural defect before building a structure. So there's a lot of things we want to estimate that we cannot see directly, and we want efficient schemes to do so. So what are we going to do today? I don't know if I'm able to cover all this, yes or no, but my idea was, first of all, let's just start about basic problem of distinguishing two or more things. So not even estimating yet, but discrimination. And then from there, we can kind of take a limit and go into the framework of local estimation theory. And there I will recall what you've learned yesterday on the classical side, and that we can upgrade all those techniques to the quantum side. And the crucial concept in that particular area is the quantum Fisher information, which is the quantum analog of the classical Fisher information. And it's the best one of all of them, to be honest. And this is for a single parameter. You can extend these techniques also to study multiple parameter estimation. And then we're going to look at some examples. Okay, so let me just start with the problem of discrimination. First of all, I want to consider this simple scenario here, where I have a black box, and this black box can spit two possible states, I don't know, rho or sigma. Now, my question is, how can I distinguish them? So if I know which are the two, so if I have a red ball and a green ball, I can try and quantify how different they look. They might have various attributes. I can quantify how different they look. So if those states are known, we can just introduce some measures of distinguishability. And these are basically distances on the space of quantum states. So I'm going to introduce two of them, and both of them will eventually be linked to protocols in the area of quantum discrimination and estimation. So one distance that I introduce first to show how distinguishable two states are is the trace distance. Between two states, rho and sigma. This is equal to 1/2. And then I have this norm here, rho minus sigma, norm 1. And this symbol means the following. Basically, I have the trace of the expectation of the absolute value of the difference. And I can expand it like this. Square root rho minus sigma dagger, Hermitian conjugate, rho minus sigma. This is one particular metric that tells me how distinguishable one state is from the other. We've not yet figured out how we can acquire the information to make the distinction. We're just saying this is one possible figure of merit that tells me how far apart they are. We will see what it means in a moment. Another distance that I can introduce, this looks even more complicated. I hope that yesterday you understood that states in quantum mechanics are described by density operators like this rho and sigma, and they do not commute with each other. So we need to be careful when we take products of them because the order matters. That's why we're writing things in such a complicated way. The other one that I want to introduce, and we will return to this later, is the Buras distance. Now this one, the square of the Buras distance between two states, takes an expression which is, I think, twice 1 minus square root, and then I have something which I'm going to call FB. This is known as the fidelity between rho and sigma. And this FB is also defined in terms of square roots and so on. Between rho and sigma is now trace. And then I have this weird combination, rho, sigma, square root of rho, all this, square. This is the quantum fidelity. Now, both trace distance and Buras distance are both measures of distinguishability. So if the two states are the same, those distances are zero. If the two states are maybe two orthogonal vectors, those distances are maximized. And you will see that the Buras distance is basically 1 minus something which is now a measure of similarity. So this fidelity is the other way around, is how much those quantum states look similar to each other. Okay, again, this one instead, if rho and sigma are the same, then it's going to be 1. Okay, so these are just two different distances. And there's many more. There's infinitely many more. You can come up with different metrics on the space of quantum states. There's some other things which are pseudo distances, like relative entropy. And many of these concepts can be imported from classical information theory, even though the geometry of quantum state is more complicated. But let's just keep these two in mind. Now let us design an experiment in which we really want to try and make a discrimination between two states. And the experiment goes as follows. So we have this black box again. Now it's a bit like, when you have playing tennis and then you have this cannon which spits out balls, and it can spit balls in two different directions. I know that it can be either one or the other one. I just don't know which one is coming. Yeah. So with some probability P0, I'm going to get state rho 0. With some probability P1, I'm going to get state rho 1. Now, these two probabilities have to adapt to 1. There's no other option. Yeah, so P0 plus P1 is equal to 1. Fine. And I only have one shot. So black box spits out a state. I need to measure what comes out. And from there, I need to make my guess. You can bet money. Is it rho 0 or is it rho 1? Okay, so what comes out of here, you measure. You have learned yesterday, I think, how to describe measurements in quantum mechanics. So it's a POVM, positive operator valued measure, right? In this case, we have just two objects to distinguish from. So our POVM will be made of two positive operators, pi 0, pi 1. Okay, and like probabilities have to adapt to 1, the POVM elements have to adapt to the identity. So pi 0 plus pi 1 is the identity operator. Now, after I've done this measurement, I will cast my guess. Okay. 0 or 1. We need to put in some kind of figure of merit for this problem. If you're going to bet some money, you need to understand what are your chances. So what we want to maximize here is the probability of guessing correctly. I know this is something that you will not have 100%. In classical mechanics, if this was just, a coin flip, then you just look at the coin after you flipped and then you say heads or tails. No secrets there. But you have a quantum state, just one copy of it and one measurement. There's no way you can exactly completely reconstruct all properties of that quantum state with the one measurement. So you are going to maximize your chances, but these chances are never going to be 100%. If you do no measurement at all, you will just, I don't know, put your money on the highest probability state there. If P0 and P1 are both 1/2, then it's really a 50-50 chance. So you have no idea. But maybe you can measure something. Depending how distinguishable they are intuitively, you can find some more clever way of telling them apart. So probability of success, it's basically the expectation value of the measurement operators when the state is rho 0 and you guess 0, and the state is rho 1 and you guess 1. So it's like this: P0 trace rho 0 by 0 plus P1 trace rho 1 by 1. Now we are going to exploit these properties here. So in particular, I'm going to use this one here. So first element is the same. And basically, I'm replacing pi1 with identity minus pi0. So P1 trace rho identity minus P1 trace rho pi0. Now I can collect something together. Who remembers what is the trace of a density matrix?
It was 1.
From yesterday. Any density matrix has trace equal to?
Right hand, please. Yeah.
1.
Very good. So this object here is 1. Excellent. And the others I can just collect together, no? So I'm going to write, so trace is a linear operation. So I'm going to write, sorry, this was rho 1. This was rho 1. Okay. So I'm going to say that the whole business here is P1. And then I have plus trace, and then I have P0 rho 0 minus P1 rho 1. All this pi 0. This is the probability of success for a given measurement. So my task is now, if that is the problem, so these are the two states, I have no control over them, they come with their prior probabilities, I've been told which ones they are, fine. We want to maximize this object. What is the only degree of freedom we have? It's in this bit here. So we want to find the most informative measurement that allows me to maximize the probability of success. So maximize over pi 0, probability of success. Now, intuitively, how does this work? I can tell you there exists a solution to this problem. And if you think of now, look at this. So this is very colorful. This combination of operators which I have forms some Hermitian operator which is not a state. It's a difference of states. We can look at its spectral decomposition, eigenvalues and eigenvectors. And it turns out the best measurement is if we project onto the positive eigenspace of this operator, right? So you don't really have to know this, but for curiosity, the optimal would be projection basically the subspace which is spanned by all the eigenvectors of this difference with positive eigenvalue. Okay? So if you maximize overall P of EMs, and I can tell you, this is not my solution, but this is from a guy called Hellstrom. And it's actually in the 70s, maybe 50 years ago. 72, 76, I don't remember. He found that you can always maximize this problem. The solution is given by this, and what you get is the following. 1/2, 1 plus, and here we go, trace norm P0, rho 0 minus P1, rho 1. This is optimal binary discrimination, or if you want, this also called hypothesis test. So you have two states, you want to distinguish between them with an optimal measurement. The maximum probability of success is given by this. So you see, it starts at around 50%, but it can be increased by a factor that depends on how distinguishable the two options are, and in a specific metric, this one. So for instance, think about it. If you put, for example, the coin toss equivalent, so P0 equal P1 equal 1/2, then this thing becomes 1/2, 1 plus, and now this P0 and P1 are both 1/2. I can factorize them out. So I get a factor of 1/2 trace norm, and this is exactly the trace distance between rho 0 and rho 1. So let me just scroll. Trace distance was 1/2 the trace norm of the difference. The best measurement gives you the trace norm of the difference with the probabilities. If they are both balanced, you gain this factor of 1/2. So this is exactly this. And so you get what we like to call operational interpretation. So yeah, trace distance is a funny measure that has a geometric meaning, but what does it actually entail in practice? Well, this kind of result tells you the trace distance between the two states corresponds to an advantage in their discrimination. So you start from the basic 50-50 chance if you have no clever measurement, but you can increase your probability of success by a factor which is exactly equal to that particular distinguishability measure, trace distance. In quantum information theory, there's a lot of results like that. At least we like to find results like that. So Andrew mentioned resource theory. It's all about, you bake some food, you put some ingredients, it comes okay. You put some extra stuff, it comes fantastic. So it's all about finding those extra ingredients which give you a better performance in tasks that you care about. This is a very, very basic task, distinguishing two states. But it turns out if you have a clever measurement, you can increase your chances, increase your return in money, if you like. And the amount depends on a particular geometric quantity. Binary discrimination. Okay. Now, this was just two hypotheses. We can extend this problem to a case in which we are only not just given two states, but many, many different ones. And I'm going to structure this a little bit so that actually all the possibilities, they are kind of belonging to a similar class. So I'm going to look at this example. And actually, this is a phase discrimination. So my scheme is now as follows. I can start with the probe. This probe enters some black box. Now, within this black box, it can be affected by some unitary transformation. Okay? But there's multiple possibilities, and I don't know which one happens. So what comes of it is a state that now depends on one of these channels which have happened this way, uj rho 0, uj dagger. And what I want to do is now I want to measure the output and guess which channel has happened. So I start with the probe, which I send in a black box. You already get the feeling of sensing something, right? So you look, something is going to happen there. The probe comes out with some information now encoded on whatever happened in there. And I want to extract this information by some clever measurement. Now, let us actually give an explicit formula for these unitary transformations. So these unitary transformations will be of the form exponential minus I theta j some Hamiltonian generator. Now H is Hermitian operator, U is a unitary operator, so it's like a gate, okay? So what does this thing mean here? Depending on the generator, we are applying a so-called phase shift to the quantum state which comes in. But the value of the phase depends on the different channels. So there's some theta 1 or some theta 2 or some theta 3. So if you want, think about, I send in a state which is oriented. You see my face as well, right? On the screen. Yeah. So I send in a state which is, say, along a line. And then it's going to be rotated around the different axes. And what I want to learn is which particular angle of rotation this state will pick. So theta 1, I don't know, maybe it's rotated 10 degrees. Theta 2 is rotated 30 degrees. Theta 3 is rotated 45 degrees, and so on. Okay, so I'm always rotating around the same axis. The H determines the axis of rotation, but the value of the angles, phase, are these theta j's, they can be different. So this problem is about discriminating between a set of pre-assigned possible real angles, phase factors theta j, each of them which can happen with probability pj. So if you want, it's similar to the previous case, but in the previous case, we only had two cases and the two states were generic. Here I'm just saying I start from some initial state and then I can implement different transformations on this state which encode a phase. And at the end, I want to guess which one was it. Okay, so again here, we need to maximize some figure of merit. Figure of merit, this can be again the probability of success. So if at the output I come with the measurement which has P of M elements by J, probability of success would be sum J. I said there are K chances, right? And then you have PJ trace, and then you have UJ rho 0, UJ dagger. This will be the output state after the black box. Yeah, this is what we call rho J, PJ. Now, this is a much more complicated problem than before. We had a closed solution in the case of just two chances. In this problem, you will see this probability of success depends on something which you can control. Yeah. So one element that you can control is what you send in the probe. And the other element that you can control is the measurement that you choose. So you have freedom to adjust the input and you have freedom to adjust the output measurement. Now, on the input side, this is where things become interesting because, so have you learned qubits and the block sphere yesterday? Or have you seen the block sphere? States of one qubit? I don't know. Yes? No? Yes, nice, thanks. Okay, so intuition, right? So intuition, this is a block sphere. Suppose that we fix my Hamiltonian to be proportional to the Z Pauli matrix. So effectively what we are doing, we are rotating states around the Z axis. No? That's what all these channels are doing, just by different angles. Now, if I send in a state which is already oriented along the Z axis, I don't know, 0 or 1, or any mixture of them, any state which is along the Z-axis, this state is totally useless for this problem because it's invariant under rotation around the same axis. So if I rotate by 10, 20, 30, 40 degrees, the state remains exactly the same. What comes out carries no information, and so my measurements, whatever I do, are completely useless. So I just have to bet on the most likely channel to happen, and that's it. Probability of success in that case is maximized by just whichever is the maximum in my distribution of Pj. And if they're all uniforms, then it's like a dice, throwing a dice, no information. So that's a very stupid choice. On the other hand, if I start from a state which is anywhere on the equator, so it's a superposition of 0 and 1, yeah, so if I start from rho 0 being some pure state where this is, for instance, the maximally coherent state on the equator, then this is my most clever choice. Because now this state is perpendicular to the axis of rotation. And then whichever transformation I apply, my state definitely changes. So I only need now to implement some measurement at the output, which is able to detect how much my state has changed. And then this we can be informed of what we have done before. So we are looking at distinguishing between some state after a rotation and the initial state without rotation. So we first need to choose a state that would be sensitive to this rotation, and then implement a measurement that allows me to see this distinguishability as best as possible. So I'm not going to write the solution to this problem, but this is just for you to keep in mind what are the players in this business here. So quantum enhanced effects already come at the choice of the inputs, because look, states which are on the axis, they would be like classical states. Yeah, it's just 0 or 1 or a mixture of 0 and 1. They have no coherence. There's no superposition in there. I'm not exploiting the full ball of the block sphere, just one axis. Anything else on that ball will be at least partially sensitive to this problem. And the best would be when I am on the equator. These are the states which have maximum coherence. So they are balanced superposition of 0 and 1, which is a genuine quantum effect. So coherence in this case helps us getting our probe sensitive to the parameters we want to, in this case, discriminate. And then we just have to top up with some good measurement at the end. Why did I start with discrimination? Because I think we can now kind of conceptually at least consider a limit in which all these choices are very close to each other. Yeah, so we take kind of a continuum limit, and we can visualize the problem like this. If you want to start from an initial probe, And space of quantum states is a complicated geometry, but just pictorially, you can ideally see that whatever transformation describes maybe a trajectory on the space of states. So here you get the state when j equal 1, state j equal 2, state j equal 3, and so on. We want to distinguish this. What if we make all those choices close to each other? Yeah. So effectively, we form a little ball. And all the states in here, these will basically correspond to rho that depends on some parameter plus a variation of that parameter. Yeah, so all the theta j all the theta j are basically distributed around one central value of the parameter. So now if we want to discriminate between all these close choices, effectively, what we want to know is really to narrow down the value of this parameter. But discrimination is a problem when you have pre-assigned fixed choices and you just want to distinguish between them. If you make these choices close and close together, ideally in the continuum limit, then your problem becomes that of really estimating the value of that parameter. In doing so, you have two chances, two main approaches. One is if you have no prior information about this parameter at all, that's a business called global estimation theory. And this is usually addressed statistically by so-called Bayesian framework. This is not what we're going to do today. Today is really what this picture describes. So we have narrowed down our choices to a small neighborhood around the value of the parameter. And within that small neighborhood, I just want to know it as precisely as possible. So this is a problem that goes by the name local estimation theory. And it's still very non-trivial. And I think this is the same that you've probably looked at yesterday already. So another synonym for this, sometimes you can find in the statistical literature, is frequentist approach, as opposed to Bayesian approach. So how do we actually make sense of this in practice? If we really have no information at the beginning, then what we can imagine is that we might be able to reset this experiment many times. The first few rounds, we kind of make measurements which are a bit random or not optimal to get some rough idea of what is the quantity we care about. And once we have narrowed it down to a neighborhood, then the procedure starts, and the remaining trials of the experiment we are going to use to really extract the best possible estimator for our parameter. So local estimation theory assumes that you have kind of already narrowed down to a neighborhood, and now we want to figure out the minimum error in estimating your parameter within that neighborhood. Okay. So what did you learn yesterday? I've been told by Anton to kind of recap a little bit. I'm hoping that I'm going to use similar notation here. Actually, I saw what you've done yesterday, so I'm hoping that this will make sense again now. What you've done yesterday is effectively linking sensitivity in a probability distribution to the variance of estimators for your parameter. Okay, so in purely classical terms, we want to estimate some parameter theta, and we have different probability distributions in this parameter. And we want to minimize the variance of this, yeah? So we have probability distributions for this parameter that depend on some random variable. And from there, we can construct estimators. And what we want for this estimator, indeed, are first, they're unbiased. So the actual mean value should correspond to the real value of the parameter. So and what you want is to minimize the mean square error, the variance of these estimators. Yeah. So you have probability distribution. From it, you can infer a distribution for your parameter. That's the estimator. Has to be as peaked as possible so that your confidence is high in estimating that thing. So you learned yesterday, I think, the Kramer-Rao bound, which says, so in the variance on the estimator for whichever probability distribution I have is greater or equal than 1 over Fisher information of your probability distribution. Now, this is the Kramer-Rao bound. I don't know if Rao is still alive. I think he might have died recently, but he was over 100 years old. Kramer died much earlier. Rao, Indian statistician, very prolific in science. So that's the Kramer-Rao bound. What is the Fisher information? It depends on the probability. And this is, well, you have various ways of defining it. I think the easiest is expectation value of the, I think the square, yeah, expectation value of the square of this operator, where this operator L theta is, what is it? Is derivative of the probability, right? Of the log of the probability, which if we take this derivative, you get 1 over the probability, and then you have derivative. Yes. So yesterday you learned, I think, sorry, I'm a bit sick today. Yesterday you learned this. What does it mean? It means for whichever probability distribution, how sensitive that probability distribution is to your parameter can be characterized by this Fisher information quantity. Now, this is usually called Fisher information. If you want, you can think of it as classical Fisher information to distinguish it from the quantum one, which we're going to introduce now. And so you see, it really looks at, so it's a derivative of log of the probability. So it's really measuring sensitivity of the probability to the parameter itself, right? So if you change the parameter a little bit and the probability distribution changes a lot, this derivative is high, and your Fisher information will be high. Fisher information is high, it means that the lower bound that you get here is smaller, and in principle, you can push it down in your estimation to achieve a smaller error. So if the right-hand side gets smaller, it means you can, in principle, lower your error and estimate things more precisely. This is now purely abstract statistics. Given a probability distribution, characterize the information that that probability distribution carries about the parameter. Right, and this information can be quantified by the Fisher information. How do we bring all this to our quantum problem? What is our quantum problem? we can always imagine setting like before. You start with some quantum state, which is your probe. This probe is sent through a box. In this box, something will happen. I don't know, a quantum channel that depends on a parameter. So by this interaction, information on this parameter is getting imprinted on your probe. Just like the case before, where we send this probe in the black box, and it could be rotated. Now we are sending it into some generic quantum channel, which depends on a parameter. And then you get here, your state that depends on the parameter is just the output of this quantum channel. Then you want to measure this. Sorry, let me just... with some POVM element. And from here, then it's just classical statistics. And then you want to construct an estimator for your parameter. So you have a probe, send it in the black box. Now, to be honest, this initial part here, the one in red, it might be optional if you like. I can start from the beginning just saying I have a family of states that depends on a parameter. But I think it's nicer to just visualize it like you start with something that you can control or prepare, and then it gets imprinted some information. It doesn't really matter how you prepare this rotator. The whole theory just looks at estimating theta from a given state that carries some information in it, right? So we have a family of states that depends on theta, might have been imprinted by some channel, right? We measure, and then from there we want to construct estimators. Now, can we just use the previous things? So we have learned some bounds related to probability distributions and variance of the estimators. Yes, we can, but we have a little bit of ambiguity here because it's true that the density matrix is effectively a quantum version of a probability distribution, but it's more than that. It contains all the possible probability distributions related to all the possible measurements you can do on your system. So we can always extract probability distributions from quantum states. The point is we have lots of ways of doing so, depending on what we measure. So we can immediately import whatever was said before by just making a connection with the fact that we obtain probability distributions which carry information on the parameter by the act of measuring your density operator. So probability distribution for theta in X is going to be the result of the measurement. Trace rho theta by X. Okay? Now you see what is the point. For every rho theta state, we can always associate infinitely many probability distributions, and which correspond to measuring different operators, or if you want, measuring your system in different bases. We always have this freedom here. Out of all this infinite freedom, we want to check and we want to figure out what is the best. Because so far, the quantities will depend on the probe state and on the measurement that you do. Yeah, so if you go back to the classical Cramer-Rao bound, you will get that the corresponding estimator here has variance which is bounded by 1 over, and now the classical Fisher information of this probability distribution. Fine. This probability distribution, let me say it here, it depends on the measurement we choose. Let me just rewrite. What is the best measurement? So far, this Fisher information is a property of the state and of the measurement. But we want to answer the fundamental question. What is the maximum amount of information that a quantum state carries about the parameter? Maximum. So how do we do this? Well, if from my state I can construct probability distributions by measurements, I just want to get the most sensitive one. So I'm going to maximize this classical Fisher information over all possible measurements that I can do on my state at the output. Okay? So I'm going to optimize here. Right, and we do the following. Oops. I define the quantum Fisher information that only depends on my state, rho theta, as the maximum over all measurements of the corresponding classical Fisher information that depends on the state and the measurement. So if I do so, this quantity is called the quantum Fisher information. Now, if I do so, come on. If I do so, let's do it. Then what I can say is that, of course, for every measurement that is not the best, my classical Fisher information will be strictly smaller than the maximum, of course. So and if that's the case, 1 over the classical Fisher information is greater or equal than 1 over the quantum Fisher information, because quantum Fisher information is the maximum over all measurements. So I can complete this inequality here with a further lower bounds, which is now 1 over the quantum Fisher information that only depends on my state. And this whole thing is now the quantum Kramer-Rao bound. That's really significant because now, and we haven't defined yet how this quantity is calculated, but now we have found the further lower bound to this error. And this is really where you hit the brick wall. That is the fundamental limit. If I really want to estimate as best as possible, if I really want to know how well I can acquire information about the parameter, I want to implement a strategy which brings my error all the way down to this red bound here, 1 over the quantum Fisher information. Okay? Now, how is this thing defined? I'm going to write the definition, and then we can go through a proof together. I have a screenshot of that proof. I don't want to do it myself because it's a little bit laborious, but let me at least define things. So quantum Fisher information for a state rho depending on a parameter theta is equal to expectation value of the square of an operator, where this operator is called symmetric logarithmics derivative. Now, how is this defined? It is very analogous to the classical case. It seems so. We just need to be careful about the commutativity of things. So you see here, classical Fisher information was actually expectation value of square of some L. And this L was indeed derivative of the log, right? So this L satisfies this equation, 1 over probability and then derivative of the probability. The symmetric logarithmic derivative satisfies a similar equation, but symmetric means that because state and its derivative don't commute, we are just going to symmetrize the expressions. So if I take probability to the right-hand side, that's how I remember this expression, my SLD satisfies the following. Derivative of rho equal 1/2, and then I have rho theta lambda plus lambda rho. Now, so this is an equation which defines the symmetric logarithmic derivative. It needs to be solved. This is called the Lyapunov type equation, if you like. And what is the problem? The problem is that rho and lambda, they don't commute. If everything is classical, so if my state rho is fully diagonal and these things commute with each other, then effectively the diagonal of the density operator is a probability distribution, and I just go back to the previous case. In that case, best measurement is you measure in the eigenbasis of your operator, and you have exactly the classical statistics. But quantum states have more. They have non-diagonal terms. They have coherence. They can have entanglement. So this thing here allows us to potentially improve our precision by finding better measurements that we can use so that we hit the limit that is dictated by the quantum Fisher information. Now, if we want to find an expression for this quantity, we can do. So Andrei was mentioning that I have worked on this problem myself. We have one of our papers was about finding compact expressions where we don't have to diagonalize the states in question. I'm not going to explain that to you. I'm going to give you the more conventional approach where you take your density operator, expand it in its eigenbasis, and then you can re-express this SLD, symmetric logarithmic derivative, and the quantum Fisher information in terms of sorry, in terms of the expression in the eigenbasis of your state. So let's try and do that. Spectral decomposition, rho, I don't know. You know, it's an eigenvalue problem. So you can always diagonalize your density operator. I don't know, call the eigenvalues EJ, eigenvectors EJ, eigenvalues will be, I don't know, PJ, EJ. And then let me expand this equation here in the eigenbasis of rho. So EJ d rho d theta EK, and then I have here 1/2 EJ rho theta lambda theta EK plus EJ lambda theta rho theta EK. Now, the eigenvalues of Hermitian operators are real. So here you can act on this, here you can act on this, and you bring out the eigenvalues. So this is 1/2. Then you have lambda J EJ, sorry, not lambda, I call the eigenvalues P. Okay. So effectively, you see, you get the same term. Okay. So from here, you can express the matrix elements of your SLD in the eigenbasis of the state. I just collect these things, multiply by 2, bring it to the other side. I get that my lambda theta is sum I and j, so ei, ej. Sorry, let me, why am I so messy now? Okay, sum j and k, ej, ek. And then what do I have? I have twice ej and here I have the sum of the eigenvalues. That's it. This is a general expression for the symmetric logarithmic derivative that for a given state, once you have expanded your density operator in its eigenbasis. And now you can plug this in the fact that the quantum Fisher information is trace of rho squared, if you like. If you like, I'm going to write the explicit expression because you can use this to calculate things. I'm just finding it one second. Yeah, so you get for your quantum Fisher information. And then you have twice So my computer is slowing down for some reason. I don't know why. Okay, so this is the expression for the quantum Fisher information now. Right, so it seems annoying to calculate. There's different ways to do it. But there's some simplifications in case your states are pure. Sorry, Andrew, what did you say? I mean, I can have just one break, or do I have to have two?
Yeah, this is a very good idea to make the no break, but maybe we have some questions for this. Maybe you can. So, do you have some questions? Yeah, we have. Yeah, please.
So my question is, obviously the best quantum case would be when we have projective measurements. Obviously it would be not a simple problem, but is there work modifying the quantum Fisher information when you restrict your set of POVMs to be in some way to more like realistic measurements?
Yeah, thank you. This is a great question. So first of all, I want to say one thing. If we are estimating one parameter like I've been doing so far, then the quantum Kramer-Rao bound can be saturated. And the optimal measurement exists, can always be saturated in the limit. So this is not a problem of one shot, yeah? We have to repeat this thing many, many times. The variance will scale as 1 over the number of times. And in the limit, it will reach 1 over number of times quantum Fisher information. And the optimal measurement is indeed, as you're right, a projective measurements, which is a projection on the eigenbasis of the symmetric logarithmic derivative. This is a nice exercise for you to actually find out that this type, if you calculate the classical Fisher information corresponding to measuring in the eigenbasis of the symmetric logarithmic derivative operator, you will find that that classical Fisher information achieves the quantum Fisher information. Very nice. Now, of course, mathematically, I can always define that basis. If I go to my friends in the lab and to the speakers of this afternoon and tomorrow, they might not be able to do so. So this quantum grammar bound and the quantum Fisher information, sometimes you use it as a benchmark, saying, this is really the best I can do. Then what you do in practice, like you say, you try measurements which are actually feasible. I don't know, in the lab, we can maybe, it's hard to do photon counting, but maybe we can do homodyne detections. For a given problem, once you determine what's the quantum Fisher information, what is the best, then you try feasible measurements and see how close your classical Fisher information goes to that limit. So we don't necessarily use all these maths to tell our friends what to measure, because in most cases they can't. And the other thing is, actually the measurements which saturate the limit are not unique. Typically, there can be more, including some easy ones that allow you to saturate the limits, even though we are guaranteed that one always exists, which is projection on this eigenbasis. There can be others which are close enough or even exactly optimal again, and they're easier to implement. And to solve this problem, sometimes it's mathematically speaking, you can optimize within some restricted sets of measurements. It's a problem of so-called semi-definite programming, so convex optimization. It goes back to what you learned yesterday. So you can try and do optimizations under restricted measurements. In some cases, it's okay. In some other cases, it's hard. Or you just forget about optimizing and test the measurements that you can implement against the ultimate benchmark. I hope this answers the question.
Well, thank you.
Yeah, thank you very much. Other questions? Do we have maybe in online audience, Anton?
Well, in an online audience, no, but I have a question actually.
Okay.
So, okay. So my question is more like experimental in terms of like, imagine that we have two different single photon detectors. One is the avalanche diode, another one is the superconducting nanowire single photon detector. Can the quantum Fisher information be used to say which measurement device is better or not really?
Let me just try and answer this way. So we have been so far treating ideal problems, let's say, no? So imagine that you have your probe, you have a channel which encodes the parameter, and then you have a measurement. So far, we've been assuming that we are free to optimize over all possible measurements there. And that is what the quantum Fisher information gives. So that one, once it's done, it already completely rules out any freedom on the measurement because it already singles out the best in principle. But if you have measurements which are performing differently, say you have some dark counts, you have some imperfections on your measurement, then you can always assume that you model this part here as maybe an ideal measurement and some other channel which is noisy, right? And so in this case, it's a matter of how we can readapt the problem. So if we incorporate the imperfection in the measurement in the general problem, then we can still use quantum Fisher information here. Oops, I didn't want to delete. We can still use quantum Fisher information here to achieve the best possible estimation of this noisy problem, where you don't only have your parameter imprinting mechanism, but you have some other mechanism that can induce the coherence, or in your case, imperfect measurement. So the quantum Fisher information, if you're able to model your measurement as an imperfect part and something else, the something else can be optimized by the quantum Fisher information, the imperfect stays there. And so then then you can compare quantum Fisher for different hardware, because you will have different problems that bring this additional noise. Or on the other hand, you start from your measurement and the measurement is given, and then you just switch the problem onto optimizing the probe states that work better with your measurement. This line of work, it's something that actually Andre is working on at the moment. And it's a kind of complementary approach where the whole optimization is done at the input, but your measurement is given.
So
Okay,
yeah,
thank you. Yeah, Anton,
thank you.
please.
So yeah, the idea for us is just to choose the right noise channel which describe the measurement device, and then we estimate the Fisher information.
Yeah. So
Is okay.
typically, yeah, this whole business assumes that you have models in place and you just want to estimate the parameters of the model. On the other hand, I think if I have time later, I will consider an example in which you have the signal and you have the noise, and maybe both of them depend on some unknown parameters. You want to estimate both at the same time. And that is also an interesting problem, which brings us into multi-parametric.
Okay, thank you very much, Gerardo. So we may take a break for 10 minutes, I believe. Yeah. And what I will do, I will now rotate this camera something like this. So this will be a microphone. So after 5 minutes, you should give a chance to Professor Adesso also to take a coffee, maybe. Yeah, but if you want to discuss something in the last 2-3 minutes to ask some questions, maybe Gerardo, you can come just before starting of this talk. Maybe some students will have questions.
I will actually stay here. I mean, I don't have to.
Okay. So, but if you want, don't hesitate, please, and something or answer some Professor Adesso questions. So please raise your hand so I should see you. Yeah. When I do not see you, please also cry. Okay. Okay, Gerardo. So you're welcome. Let's continue.
Thank you. So I had promised I would quickly just show one way of deriving this quantum Kramer bound. Now, this is a copy and paste that I got from effectively this second reference here. Now, Rafał Demkowicz-Drobczewski is possibly, in my opinion, the most expert in the field of quantum metrology that we have. Actually, both Matteo and Rafał, they are people who have worked on these problems for 20 years or more. So Rafał has some notes from his lectures, and I think he's writing a book. So I hope that this book is ready soon because it's a very nice textbook on the field, which at the moment is missing. So once this book is ready, then I would recommend to everyone. But from his notes, let's just try and give an idea what are the ingredients to derive this quantum Kramer bound we were writing here. So this, I think, F is what I call I. So the classical Fisher information, as we said, is the expectation value.
Sorry. Could you make a little bit larger on your screen? Zoom a little bit.
Oh, yeah, of course.
It's here. Oh, okay. So perfect. Thank you very much.
Thank you. Sorry. So the classical Fisher information for a given probability distribution is equal to the expectation value of the square of the classical logarithmic derivative. And remember that we had just defined the probability distribution as being trace of measurement operator on our state. Of course, the expectation value is going to be the integral times the probability of the quantity we care about. So you do this, and then you insert in here the definition of the quantum symmetric logarithmic derivative. So you bring in the lambda operator in your derivative of rho. Okay, so far this is just classical Fisher information for a given measurement, but we are re-expressing derivative in terms of this new operator. Now, because everything is Hermitian, you can effectively rewrite this thing in terms of just real value. You can just add and subtract these things here, and then you have a bound inequality like this. And now you use, and I think for all of these Kramer type inequalities, you have to use Cauchy-Schwarz. There's different ways of doing it. So this is done with respect to the Hilbert-Schmidt product between two operators. Now, if you look at this quantity here, you have a product of 3. So we can do some clever tricks with the square roots. And then you have one operator being square root of the measurement, P of M, square root of rho. The other one being the one that takes care of the rest. Yeah, so you are expanding this one into 2 square roots and the density operator also into 2 square roots, rearrange with the cyclic properties of the trace, and then you can do this. And then we get the application of Cauchy-Schwarz gives us this expression here. If you bring this back, I mean, you don't have to follow all the calculations here. They're going to be pasted in the file. You effectively get classical Fisher information for any given measurement is given by effectively this expression. And this expression is the expectation value of the quantum symmetric logarithmic derivative, exploiting the fact that POVM elements are complete. And that's it. So for every possible measurement, your classical Fisher information is upper bounded by the quantum Fisher information, which we have defined before. And this gives us the complete quantum Cramer bound as I have written before. So this was a little bit quick. You can try if you want yourself, but it was just for completeness. Now, what happens for pure states? For pure states, you can get simplified expressions. This, I think it's a nice exercise for you to do. What you can exploit the fact that the pure state can be written as a projector. Okay, so this state will depend on the parameter, of course. And because it's written as a projector, then you also have that rho theta square is equal to rho theta. That's only for pure states. These are rank 1 projectors. If you use this information and you put it in the definition of symmetric logarithmic derivative, then you have nice things. And I leave this as an exercise. You arrive at the following. Quantum Fisher information for a pure state is equal 4 times, and then I have here this is the derivative, I'll write explicitly, minus where I'm using this notation. Now that's quite interesting, and it's a nice compact expression. So it just depends on the overlaps between your state and its derivatives. And this is even more intuitive if we consider the whole problem again, like one of you was asking, in which the channel that encodes the parameter is unitary. Okay, so we start from some state psi 0. Then you have here u theta. It's now a unitary operation. So it's e to minus I theta, and then I have the Hamiltonian. This Hamiltonian is the generator of my transformation. Like before, when we were picking sigma z and rotating around that axis. So this gives me psi theta, which is just u theta applied to psi 0. And then we measure. Now, if you do this, and you plug this into the expression above, you obtain, for this case, that the quantum Fisher information on the parameter psi theta, and this is exactly what was said. It will only depend on evaluation of a particular quantity on the input state, because this is a unitary, so you can re-embed it. You can do this now, so we can actually do all the passages, right? So at least start doing some derivatives here. So psi dot. This is now, so sorry, without the dot, right? This is just e to minus I theta h psi 0. And so the dotted version, that's an exponential, so it's an easy derivative. You have minus I h. My computer is getting slower and slower. I don't know why. Then, and then you have the same thing, huh? Yes. And then you keep going. Take all the expressions, all the overlap, and put them in the formula above. You will find the quantum feature information for this problem is just 4 times. And now you have the variance of your Hamiltonian generator evaluated on the initial state. So explicitly 4 times psi 0 . That's a very interesting problem and a very interesting result. So what do you actually need here? If you want, you can think of it as it's a bit like an uncertainty relation. Yeah, if we bring this into the Cramer-Rao bound again, we have the variance of my parameter is bounded by 1 over 4 times the variance in the generator of that parameter. So you might think that the product of those variances is somehow bounded from below. It's a bit like a time energy uncertainty relation. So if I want to maximize the precision of estimating a phase that is generated by a certain Hamiltonian operator, I want a probe from the beginning that has a maximum variance in that particular transformation. And this brings back to the situation we had before. So if I wanted to estimate rotations around sigma z, I don't pick a state which is already aligned with sigma z. I pick a state which is orthogonal to it. It's a maximum balance superposition of 0 and 1, because that one will have a maximum variance in the sigma z operator. So this thing is reflected in the expression for the quantum Fisher information. For this simple case, unitary model, pure states, precision is the variance of the generator. That's the best you can do. When you have mixed states or when you have non-unitary channels, then you can, as we were saying in the break, so you can kind of upper bound your quantum Fisher information by considering all purifications of your model. So you can eventually bring back your results to this unitary case, but you just need to consider all possible dilations incorporating system and environment, calculate quantum Fisher information on this, and then minimize over all possible extensions. Of course, if you have decoherence, you lose some information to the environment. If you were able to retain that information, then you would extract even more from your problem compared to what you can achieve if you're only limited to the system. So you can always upper bound the quantum Fisher information by considering dilations and purifications. So in general, quantum Fisher information is a convex quantity. So by mixing, it usually goes down. And it is additive on tensor products, which means that if you have quantum Fisher information for some state, oh, pen battery low, that's really bad. I should have charged it while I was on the break. I'll put it here for a moment and see what happens. I didn't consider it wouldn't last, sorry. I hope it will last until the end. Anyway, so tensor product, this one is just n times quantum Fisher information for one parameter, one copy of the state. And we will return to this once we talk about Heisenberg scaling versus standard quantum limit in a moment. So what I wanted to say here, I think I need to speed up a little bit. There's been lots of interest in the fidelity. So what is the relation between quantum Fisher information and the fidelity? we might think of the following problem. So you start from your row, then you get here state that depends on the parameter theta. And then you may change your parameter a little bit. And then the question is now, I have a probe and it imprints information, it gets information on a parameter. And then I tweak this parameter a little bit, my state will change. Is there some relation between the rate of change of my state when I change a parameter and the information encoded in the state on the parameter? The answer is yes. The answer is yes, because so we were seeing that we have introduced two ways of distinguishing states. One was the trace distance that we have found quantifies distinguishability in state discrimination. And then the other was the fidelity that is related to the Bure's metric. So what it turns out that we have the following result. Fidelity between state rho depending on theta and state rho depending on theta plus d theta. So that was the quantity with all the square roots. We have seen there's a simplified expression. Still, you need to expand that. It's a series expansion. And if you do it, then you find, of course, to the lowest order, the two states are exactly the same. Yeah, so it's 1. Order 1, it's typically 0. So you need to go to the second order expansion. Second order expansion gives us 1/4. And here we go, quantum information of rho theta, d theta squared, plus terms of higher order in d theta. So what does this thing mean? Our quantum Fisher information that was defined purely statistically actually has a geometric meaning. It tells us how fast the fidelity drops when we change a parameter. So it tells us how fast my state is modified when I tweak the parameter. And that's a very nice intuition, because what makes a good probe, right? So if I have a scale and I want to measure things very precisely, I want to be able to see the numbers change when I just, adjust the weight by micrograms or whatever I like. So a good probe is sensitive to the parameter if I can spot the difference even when I make small changes to the parameter. So the quantum Fisher information not only has a statistical meaning, yeah, it limits the error in the estimation, but it has an intrinsic geometric meaning. And this thing can be formalized further. So actually one can construct, I don't know if any of you likes differential geometry. One can construct the Bure's metric on the space of quantum states, and then one can see that the infinitesimal element of the Bure's metric is just proportional to the quantum Fisher information with a factor of 4. So from here, this gives an alternative way of calculating the quantum Fisher information from the fidelity, effectively. So if you have a quantum state depending on a parameter, and you can check how the quantum fidelity changes with this parameter, then we have the quantum Fisher information for a state rho. If I remember correctly, it's something like so -4 limit for h going to 0. And then I have second derivative of square root of the fidelity between rho theta, rho theta plus h. So that's an alternative expression. Depending on the problems, sometimes you can just take your density operators, diagonalize them, calculate the expressions as before. Some other times you have a simple formula for the fidelity. For instance, in my case, I've worked a lot on continuous variable systems, and you have a formula on the fidelity between arbitrary states of harmonic oscillators, Gaussian states. From there, that is very helpful when you want to calculate, for instance, the sensitivity of a thermometer. I think Andrew mentioned yesterday, temperature is a parameter you can estimate. You have a bath, you want to or a sample, you want to estimate temperature of that sample. What do? You send in a probe, wait for it to reach thermal equilibrium, and then you have to measure the probe once it's thermalized. Once it's in a thermal state, the sensitivity to the temperature can be calculated by the quantum Fisher information in the thermal state. Thermal state is an example of a so-called Gaussian state. So the easiest way to do so, because these are states of infinite dimensional systems, the easiest way to do so is through the fidelity. You calculate it, and then it turns out that the quantum Fisher information is just proportional to the heat capacity. That is a seminal result, which was found maybe 10 years ago, and now there's a lot of developments in the field of thermometry. But we know what is the best thermometer allowed by nature, and its performance can be quantified by the quantum Fisher information. So it really tells you the response of your probe to a change in temperature. And this all comes from this geometric interpretation here. Okay, so I hope this was interesting. And this just gives alternative ways of calculating this quantity that we all care about. Now, so far it was for one parameter. I want to move on to multi-parameters, just at least mention what's the situation here. And if there are no more questions, I will just proceed that way.
Yeah, do you have questions? In the audience? Or Anton, do we go online?
Yes, there is a question from the
Yes,
audience.
there is. Yeah, please.
Are there cases?
Other cases? Yeah.
Yes. In that case, then the quantum Fisher information is 0. In that case, it means that your probe was really bad, right? So, for instance, what I was saying at the very beginning, if you want to estimate phase generated by sigma z, and you start from an eigenvalue of sigma z, then whatever you do, changing the parameter leaves the state invariant. So its fidelity with it, it's always 1 because the state is the same, no matter what. It's independent of the parameter. In that case, your quantum Fisher information is 0, and that is the worst possible thing you can get. So your state carries no information on the parameter. On the other hand, you want the quantum Fisher information to be as high as possible, which means the change is as big as possible when you tweak the parameter a little bit. And that's a good probe. Thanks.
Okay, thank you very much. One more question from audience. So, please. Oh, just a moment. Yeah, it worked.
Maybe not so much a question, but a comment. It was really nice to see the expression for quantum Fisher information of the pure state to pop up, because I've already seen it in terms of the purest metric before, and like there's a nice book by I think Karol Rzeszkowski, and it's called like quantum
Geometry of quantum state.
Yeah.
Yeah, it's a beautiful book.
It's a really nice connection.
Yes. Thanks. I mean, that book is beautiful. This is the guy who knows everything about geometry. I mean, he has so many metrics in there, so many beautiful pictures. Yes, that is a fantastic book. Yeah, thanks for the suggestion.
Yeah, okay.
Yeah, so
yes, thank you. More questions?
There is also, of course, this thing is not so special to quantum, right? So there is a similar interpretation of the Fisher information in the classical systems. It's related to the Fubini study metric, the classical Fisher metric as well. So actually, if I have to be honest with you, in the quantum case, there is not one unique quantum Fisher information. So the one we have been working on all the time is the largest of the family, but there is a whole family of quantities that can be considered as the quantum analog of the classical Fisher information at the metric level. And they all are characterized by, this family goes by the name Pets, Moronkova, Chenkov. They're characterized by some functions that define different ways of calculating averages of quantum states. So you can have the geometric mean, the arithmetic mean, and anything in between. The quantum Fisher information is the largest of the family, and it has a very nice property that for pure states, all of these families reduce to the variance. All of them, they reduce to the variance for pure states. For mixed states, they can be different. So one member of the family is called skew information, Wigner-Yanase skew information. But quantum Fisher information is larger. And actually, this was discovered only recently, surprisingly. It can be defined as the convex roof of the variance. What does it mean? So if you take any mixed state, you can decompose it in terms of ensembles of pure state with some probabilities. And there's many, many ways of doing so. Yeah, you can just mix pure states until you obtain your density matrix. Out of all possible decompositions, you can minimize the variance of the generator weighted by the probability distribution that forms these decompositions. This procedure is called convex roof. Now, the quantum Fisher information corresponds to this convex roof procedure, where you basically look at the minimum variance over all possible realizations of your mixed state. And the other members of the family, they are smaller than that, so they don't have this nice property. And this is interesting. It was found, I think, by Gezatov and Dennis Petz himself. And there's been several proofs, maybe the past 10 years, I would say. Okay, thanks. Right, so this was single parameter. Then, of course, it's just an interesting generalization to go beyond single parameter and to look at, I'm just going to mention maybe some formulas and structure here, where we want to estimate more than one. Okay, so what happened? Because what happens in the multi-parameter case, again, I like to start from some neutral probe. Now there is some mechanism here which depends on a vector of parameters, yeah? And then, so you obtain your state that now depends on all these parameters, and then you have to measure. And we want now to construct estimators for all these parameters. Now, in the classical case, there's no big problem. Okay, you can look at questions of statistical independence if you like, but it's not that basically one parameter is necessarily incompatible with another, because in principle, we can measure them all with arbitrary precisions. In quantum cases, it's not true anymore, because you can have parameters which do not commute, they're incompatible with each other, so there might not be one universally optimal measurement that gives us the best estimation of all these parameters in one go. You can always decide to, I don't know, if you run this experiment many times, you can split batch of probes you use for estimating the first one, batch of probe for estimating the second one, and then you kind of decouple the estimation. But sometimes you can gain if you try and do a simultaneous estimation, provided that you can show that there is compatibility in doing so. So what happens here, all of the previous results extend. They just go, basically they become matrix inequalities. Okay, so instead of just the variance of one parameter, we have the covariance matrix of this vector theta. This is a matrix with element ij being expectation value of theta I, theta j minus theta I, theta j. Okay, and so we have now that this matrix, it's a matrix, is bounded by the inverse of the quantum Fisher information matrix. And how is this quantum Fisher information matrix defined? So this is now, it's a matrix inequality, and that's the multiparametric quantum Kramer-Rao bound. So this quantum Fisher information matrix is defined similarly to before. elements this is supposed to be some kind of weird F, yeah? Elements ij, they're just trace row that depends on all the parameters, lambda I, lambda j. So you have products of different symmetric logarithmic derivatives that enter here. Each one of them is defined implicitly by an equation like before. So the rho d theta j equal 1/2 rho and that's all it is. Now, this seems a little bit scary, and of course you can have many parameters, right? If you want to bring something closer to what we had before, this by itself is a matrix inequality. If you want to bring it again in terms of bounds on the errors, the easiest thing we can do is just take the trace, take the diagonal elements, yeah? Take trace. And so the trace of the covariance matrix is just the sum of all the variances. So sum j variance on the parameters j is bounded by trace of the quantum Fisher information matrix inverse. So you have to be careful here, right? Because you first calculate the quantum Fisher information matrix from the prescription before with all the symmetric logarithmic derivatives. Then you get the inverse, and then it's the trace of the inverse which actually gives a bound on the errors. Of course, here in this expression, I'm taking errors on each parameter with the same weight. You might also generalize this particular thing by including different weights so that, I don't know, you maybe care about more minimizing the error on one parameter and you don't care that much about the other one. Examples of multiple parameters can be various, right? So even if you just go back to the qubit on the Bloch sphere, when we were estimating phase around Z, that's effectively just like estimating a magnetic field pointing in the Z direction. But you might want to estimate a magnetic field in all directions. So it has components on sigma x, sigma y, and sigma z. And these three things are incompatible. So you need to look at what is your best bet for trying to minimize the error on the estimation of all these things with some suitable measurement. Now, for a single parameter, we said you can always saturate the Kramer-Rao bound, and I even gave you one explicit measurement, which is the projection on the eigenbasis of SLD. Problem with this expression here is that this quantum Kramer-Rao bound is not guaranteed to be saturable. So it gives a lower bound, but it can be ideal. You might not be able to reach all the way down to the right-hand side, which is the inverse of the quantum Fisher information matrix. Whether you can do that or not depends on a so-called compatibility condition. And this is a non-trivial result. So the quantum Kramer-Rao bound for multi-parameter is saturable if and only if the following happens. The expectation value of the commutators of the SLD operators vanishes. So intuitively, what does it mean? Now, imagine if these parameters are generated by, we can also go back to just unitary, no? So this magnetic field case, that's actually not a good example, but if they were generated by Hamiltonians which commute with each other, then it means that I know that those parameters, I know that there exists a common eigenbasis which diagonalizes all those operators. And so I know that there exists one measurement basis that allows me to extract all the information from all these parameters at once. So if they commute, and the SLDs are the ones that we care about because the usual optimal basis is the eigenbasis of the SLD. So if the SLDs commute, then I can all diagonalize them in the same basis, and I'm just going to measure in that basis. So this one direction is easy. The other direction is non-trivial because actually it turns out you can still estimate, even though they might not commute in general, but they need to commute on average on your probe state. So you have to find some probe state such that effectively the SLDs behave as if they were independent, even if they might not commute in general. If that's the case, then your whole problem becomes compatible, and there exists one jointly optimal measurement for which you can achieve the simultaneous estimation. So later on, I want to show an example of a multi-parameter case in which I want to estimate basically signal and noise at the same time. I'm not going to do it now straight away, but I'll do it in a moment. So I will return to this after I have introduced the next bit. But this theory is a bit more complicated, and this is a compatibility condition which one needs to check. Otherwise, the Kramer-Rao bound, even the quantum Kramer-Rao bound, becomes less meaningful. Yeah, it's an ongoing field of research to work out exactly how close you can reach, what types of measurements you are limited. So this goes back to a question that someone asked before. What if you're limited to certain measurements? This is even more relevant in this case, because even if you are completely unconstrained, you might not be able to reach down to the quantum Kramer-Rao bound limit. Even more so, if you are constrained, then we need more informative bounds. That's an interesting problem. This work's ongoing. We're not, of course, doing much here in these 3 hours, but there's a lot of work trying to achieve bounds which are more meaningful for finite sample size and for multi-parameter cases that really tell us where we should aim. Because if I evaluate this lower bound, it might be very far away from anything really possible. So it's not really a good benchmark in general, while the single parametric case, it was. So we need to be careful. All right, so what I wanted to move to, and then return to this example, was the role of quantum resources. So everything we have done so far was basically taking care of the optimization on the measurement end. And this is what is done by the quantum Fisher information. Once we've done that, then we can forget, in principle at least, for one parameter at least, forget about the measurements. And now we just need to think some useful initial states, and then the optimization of our measurements is taken care of by this theory. But I want to go back to the situation of the initial state now. And the choice of the initial state may be simple if you just assume in your mind one round. We already figured out how things work, for instance, on the Bloch sphere. That's perfectly legitimate. But where the real advantages come from that define what is the field of quantum metrology come into play when we have multiple rounds of this parameter that is being imprinted on your state. And here we have different geometries that we can consider. So let me just do 3 scenarios here. Okay, so and this we can work out explicitly. So my initial state, so I have 1 qubit. Okay. My Hamiltonian is just sigma z. I'm sorry, I forget all the hats. From yesterday, you learned from Andrew, you need to put hats on all these operators. Many of my operators deserve the hats, but I'm just being sloppy, sorry. So I'm considering rotations around the z-axis by some angle theta. So single parameter estimation, back to single parameter. My unitary depends on theta, is e to minus I theta sigma z over 2. And I'm going to consider just, at the moment, 1 qubit only. So my initial state is clear for this problem. We have said it 3 times now, that the best states are on the equator. So I'm just picking one of them. the plus state, which is 0 plus 1 square root of 2. Okay, so this is a case which we have pure states, unitary models, no problem. Let's calculate quantum Fisher information. So my scheme is as follows. I prepare my state, I get the unitary, I measure. Okay? So quantum Fisher information in this case is 4 times the variance of the Hamiltonian on the initial state. So my Hamiltonian, we said, is sigma z divided by 2. So h squared is 1/4 sigma z squared. Now sigma z squared is the identity. So this is 1/4 the identity. And of course, we are measuring on this balance superposition of 0 and 1. So what is my state, first of all, anyway? So, oops, sorry. No, I don't need the evolved state. So the initial state is all I need. So we have 4 times 1/4 times, of course, 1. And the other term, we have this. But the expectation value of sigma z on 0, on the superposition 0 plus 1 is 0. So minus 0 here. So the quantum Fisher information for this one round of estimating the phase generated by sigma z is 1. Now, what I said before is that the Fisher information is additive. So if I repeat this experiment n times without any correlation between the measurements, so NIID, independent identical distributed sample, prepare my state, do the unitary, measure. Prepare my state, do the unitary, measure. Prepare my state, do the unitary, measure. N times, the total quantum Fisher information will be just n times 1, n. Now my question to you is, if my resource is the number of times I'm going to apply this box, yeah? The number of times I'm going to apply this unitary transformation, that's my resource. In this case, n. I have n boxes. I want to combine them any way I want. Can I do better than this? First attempt, I keep the scheme as it is, but actually I change the input state. So I will use entangled states. Do you know what entangled states are? So these are states which share some strong type of correlations. In this case, I'm looking at n qubits. And so the most direct generalization of the plus state would be what we call a GHZ state. So now these are all entangled. Then, okay, here, to be honest, for this problem, independent measurements are still optimal. But in principle, I might have to do, if you want, some collective measurement. Not in this case, I can anticipate. Okay, so my initial state now is this 0, 0 plus 1. Okay, that's the whole thing. And now, what is the general? We are still using. No, this I don't need. So we are still using all unitaries in parallel. So the transformation is U tensor n, and this is generated by Hamiltonians which go like, so the sum over J of sigma Z half tensor identity for all K different from J, if you like. So effectively we have Hamiltonian on the first qubit tensor all identities plus identity, Hamiltonian on the second tensor all identities plus and so on. Okay? Now, what do you think will happen in this case? We can calculate things any way we like. We can calculate things, for instance, by means of looking at the derivative or by looking at the Hamiltonian generator. It's a very nice exercise that you can do. Let me see if I have it here. The expression I wanted to use, but I don't want to spoil it. What happens is, when we are picking up a phase difference, yeah, this is going to appear amplified n times at the amplitude level. Okay? And so when we calculate the variance of the generator in this case, there's an extra factor of n, which comes from this. So the quantum Fisher information in this problem, and I hope that you can calculate it any formula you like, is going to be now not n anymore, and that's the magic, n squared. This is what we refer to as the Heisenberg limit. While the previous one, when things scale like n, sometimes is referred to as the standard quantum limit. So we have not changed much of the implementation of the circuit. We're still running things in parallel here. And the quantum Fisher information is still taking care of optimizing over the measurements. But we have an extra degree of freedom that so far we never really talked about. And this only comes into play when we have combination of multiple rounds of the experiment. So normally, if we just let each run be independent, we have quantum Fisher information that scales like number of resources. But if we exploit some quantum properties, in this case, entanglement across n qubits, then we get a quadratic enhancement, which would then translate into a quadratic reduction in the error that we can achieve on the estimation of this phase. And it's intuitive, but the fact that these objects are all correlated with each other, when they pick up a phase difference, this is amplified across all of them. Now, this is an idealized situation. In practice, this state is very fragile. If one of the qubits is compromised, the whole state loses all of its entanglement properties, and so it will collapse back into actually a very bad state that has no sensitivity at all. So in real experiments, it's always a matter of checking if we can find some initial states which are maybe more robust to errors and losses, and they might still be able to come close to this quadratic limit, but not necessarily be exposed to losing it all. So this one is the holy grail of the whole business of quantum metrology, although there are nice papers that show that this limit is really elusive. So on paper, it works. In practice, there's lots of noise mechanisms which actually make you lose this advantage. but in principle, we can do it. Now, I had to go all the way to entangled qubits. Actually, I want to say this is not necessarily the only thing you can do. There's an even simpler scheme, which still uses n boxes and still works with just one qubit, right? Which one is it? The second scheme. Second scheme is a sequential scheme. So we still start with just one qubit in the plus state. And then what we do, all these n boxes, we run them one after the other. Instead of in parallel, we run them in series. And then we measure the end. So these are still n boxes of the usual unitary. So now here, what is my total unitary combined is this u theta to the power n, not tensor product. Before it was in parallel tensor product. Now it's to the power of n, which means that the Hamiltonian itself picks a factor of n. So E minus I theta over 2 n sigma z. And so what we have to do, we have to calculate now variance of this object here over the single initial state. So before n boxes in parallel, but we required multipartite entanglement. Here, n boxes in series, we just require one state with coherence, and the Hamiltonian has been amplified. Okay? And what happens in this case, of course, when you do the square, right? So we have to do the delta square of this Hamiltonian. And this is now n squared. Oh, sorry, the factor of 2, I forgot. So the variance of this Hamiltonian is now 1/4. Then I have this factor n squared and then 1, because sigma z squared is still the identity. And so I get exactly the same thing. So for this scheme, again, I have Heisenberg scaling. So there's a very, very nice equivalence between two quantum resources. In this case, my quantum resource is simply coherence, superposition in the eigenbasis of the Hamiltonian. In the previous scheme, my resource was entanglement. For the purpose of estimating parameters encoded in unitary transformations, these two fundamental quantum resources are exactly equivalent, in the sense that the calculations give rise to the same precision bounds. Both of them beat the standard quantum limit by a quadratic factor. Both of them achieve the Heisenberg limit, which is the best that we can achieve. It cannot be surpassed. The problems, the inequivalence between them comes when we have realistic conditions. So for instance, that entangled scheme is a lot more fragile than the sequential case. If you want, you can add some cost considerations. I could say, I don't know, maybe it's a lot cheaper to prepare one qubit only in a superposition state and then just run the boxes after each other than to create entangled states that require interaction between all of them. On the other hand, you might think of the other way around. If time is of the essence, the parallel scheme runs in one go. The sequential scheme is effectively like running this thing n times the time. So there's a lot of trade-off to be made in the business of quantum metrology if you really want to make some sensible estimation of resources. This is, again, another area of open, very open investigation. It's something I'm interested in, really trying to not just, follow the ideal of whatever is the best in nature, but see if any improvement is worth it and that we can make it sustainably. So that's something that I hope that in the future will be a lot more discussed. But what I've shown you here is that there are two schemes for phase estimation which ideally work at the same level and both achieve the Heisenberg scaling. Now, do you have questions on these two examples?
Yeah, questions? Do we have online questions, Anton?
Oh,
Probably
we
not.
don't.
Okay, very good. Okay.
Oh,
So of course,
okay.
then you can go and hybridize everything, and people are looking at this now. So, okay, we might still have n boxes, but we might have situations in which the unitaries are not perfect, maybe. Sorry, did I lose my screen? I don't know. I see Anton on the screen. I don't know why. Okay. And so I don't see the class anymore. I don't know why.
Yeah, this is
Oh, no, sorry. I'll just select it. Okay, very good. Fine. Sorry. Yeah, so you can always think of situation in which you maybe want to hybridize a little bit. You want to distribute boxes between some entangled states that maybe do not cover all the qubits and some rounds which go in parallel. And depending on the situation, you might want to find the optimal geometry of your network. Yes, thank you, Mohammed. Yeah. This is a nice problem, optimizing geometry of the networks. But this problem becomes relevant in the moment in which you start to input some imperfections in the problem. If everything is ideal and unitary, it's really mathematically equivalent. When you have some noise, some of the schemes are more robust than others to the noise. So, which brings me back to what I wanted to say before, which is estimating multiple parameters, or at least considering estimation in the presence of losses. So I think I'll probably go back to this tab. And let's see if we can run this example explicitly. No, I think I can continue where we are. Yeah, I think there's no sense just going back. Okay, so let's do the example here. What I want to do now, same problem as before, but in a realistic situation. So there are two mechanisms at play. One is the unitary, e2 minus I theta sigma z over 2. And then there is some noisy channel that depends on some probability, lambda. And this channel does the following. Actually, let me write it as epsilon. This channel does the following. So with probability 1 minus lambda, it does nothing to my state. And with probability lambda, it completely dephases my state into maximally mixed state. So this one is a unitary. Phase shift. This one is a depolarizing channel. My handwriting is becoming worse and worse over this tree. This looks like a camel channel. Okay. Right, so we want to estimate the signal here, but there is some noise acting on my system. Now, of course, we have plenty of ways of modeling this. Typically, we can run master equations. We can do a continuous time model in which at the same time noise is acting all the time. Or we can just, for simplicity, to keep in the language that we've used so far, we can discretize our sequence of operations into, you have signal and then the noise acting, and then signal again and then the noise acting, okay? That's fine because actually these things commute. As you can see, the polarizing channel is independent of the phase. So we start, so I'm going to do the sequential case. And then if you like, you can run the entangled parallel case and see if it changes anything. I haven't checked it myself. So in the sequential case, we start with the state, and this is going to be still the plus state. Now we have my unitary, and then we have this noisy channel in sequence. Overall, this is the block which is happening. And this is the block I'm repeating n times. And then I measure, okay? Every time it's unitary and the noise. Bam, bam, bam. So this is an interesting situation. It's a lot more realistic now. So if lambda is, what is it? 0, that's the probability of the polarity. If lambda is 0, then the noise is not happening. If lambda is 1, then I'm completely destroying my state already after one round. Okay? So what we want to do here, we want to calculate everything. Now, let's start and try to do things step by step. This whole thing is repeated n times. So initial state, it was plus, plus. So density operator, 1/2, 1, 1, 1, 1. Excellent. Now, we apply the unitary. So u theta rho u theta. Okay, what happens? It was proportional to sigma z, right? So my unitary was something like e2 minus ei theta over 2 and the e2 I theta over 2. Apply to rho. And then I have the same thing here, transpose. You can do a bit of matrix multiplication. So, right, and so what we get the following expression. 1/2, 1 e minus I theta, e I theta, 1. This is the same state we would have obtained before. Okay? That's after just one round. Now, we apply the channel. Okay? So, epsilon lambda applied to this. This gives us our state rho that now depends on both parameters. So it's a multi-parametric problem. You can actually, I mean, I don't have to do the calculation, right? So it's going to be 1 minus lambda times the previous one plus lambda over 2 identity. You group things together, you get the following. 1/2, 1, 1 minus lambda, e minus I theta. And then 1. So you see the effect of this channel. So what we were saying before is that our resource for the sequential case is coherence. The fact that the state is a superposition. And we wanted maximum coherence. And for a density matrix of a qubit, you can read off the coherence from the off-diagonal elements. So this channel is negatively affecting my coherence terms. It's impacting the off-diagonal elements. So clearly it's going to create me a problem. Yeah, if I didn't have it, everything is perfect, Heisenberg scaling. Because of this, now what happens? This is just one round. Now I run another round. Yes, I pick up more information on the signal, but then I get an extra damping factor on my coherences again. Then I pick up more information and then I get more damping factors. So if I do this n times, it's a very, very nice exercise, I think. Given the structure of the density operator, you can kind of guess what happens. After n times, applying signal and noise, sigma and noise, sigma and noise. So the signal in the phase gets amplified by a factor of n, and the noise also gets amplified by a power of n in this case. So your sigma now theta lambda after n times is the following. The diagonal doesn't change. And then you have here 1 minus lambda to the power n e2 minus I n theta. And one. And the same here, 1 minus lambda to the power of n e2 I n theta. That's it. And this is the state on which we measure. Okay? So now we have all the formulas from before. And we can calculate the quantum Fisher information matrix. We can calculate all the symmetry logarithmic derivatives. We can calculate everything. In principle, we can look at two things. One thing is we want to estimate the phase, and there is this noise which is annoying us. So maybe we have already assessed that we have a certain amount of noise. We assume that quantity is known. It's just a nuisance on our parameter. In this case, it reduces to a single parameter estimation problem, but for a non-unitary model. What I was asked during the break, we cannot invert this anymore because this noise is going to be non-recoverable. Okay. On the other hand, we want to actually see if we can estimate both parameters. And this can be for a matter of controlling whatever is happening there. If we can get information both on the signal and the noise, maybe we can then implement some error correcting scheme that somehow filters out the noise as much as possible and tries to re-amplify the signal as much as possible. So I'm not going to go into that, but that's a very active line of research. So in metrology, sequential parallel schemes are equivalent without noise. After noise, things happen. And you can somehow counteract the noise by actively controlling your thing, if you know what you're fighting against. Yeah. So estimating signal and noise in this case is actually something which makes sense. Now, I think I have the final results here for all the SLDs, but I'm not going to do all the calculations. But in principle, if you just revisit this in your own time, with all the formulas that have been introduced, you have all the material to calculate SLD for the phase, SLD for the noise, bring them together, construct the quantum Fisher information matrix. If I have not done mistakes, the final result should be the following. Quantum Fisher information matrix evaluate on the state after n rounds, depending on theta and lambda in this order. It's interesting because it's diagonal. So I don't have off-diagonal terms. So these parameters are statistically independent, which we kind of expected because, as I said, they commute. N squared 1 minus lambda 2n. And the other one is a bit more complicated. N squared 1 minus lambda 2 n minus 1. And this is 1 minus lambda 2n. So now remember what this means. Because the quantum Fisher information is already diagonal, the inverse is easy. And actually the diagonal elements straight away give us information about the parameters that we care about. They are this is a case in which they are statistically independent. So we can and we can also verify that the compatibility condition is satisfied. So you can verify the following. A trace of rho SLD for theta and SLD for lambda. This thing on our state is actually 0. So they are compatible. We can estimate both parameters in one go. And then, of course, move on to clean up our lab. But how these things look like, you can then, once we have verified that they're compatible, you can, in principle, saturate the Kramer-Rao bound. And we can split it separately on what you get for the signal and for the noise. So here, in this case, oh, what am I doing? In this case, this one would correspond to the quantum Fisher information for the signal, and this one is the one for the noise. For the noise. How do they actually look like? Can you more or less figure out the functional form? The one for the signal, I think, is the most interesting of all. No, because before we were saying when there is no noise, it's just n squared. And this is actually recovered if you put lambda equal 1. Sorry, lambda equal 0. So 0 probability of depolarizing is just n squared. But because you have some non-zero probability, the plot is going to run like this. Here is the number of rounds. Here is the quantum Fisher information for the theta. Now, the ideal case was, this is when no noise. In the real case, you're going to find something like, let me just do it better. Sorry, can I just delete this? I don't have enough space. I don't know. I'm giving random numbers, yeah? I don't really know exactly how it goes. That's qualitative. So, in this case, you lose the advantage at some point. Because what we were saying, the more rounds you do, your signal is amplified, but the noise piles up as well. So it starts quadratic, then at some point, it will basically go linear, like in the standard quantum noise. But then it actually picks up to a maximum. If you keep doing it, then you lose everything. So there is an extra optimization to be made in this case. For realistic scenarios, you need to find the optimal number of rounds that maximizes your quantum Fisher information for the quantity that you care about. Okay? So if you wait too long, then you do even worse than for the states without coherence or anything. So that's interesting. Then you can also plot the other one, the one for the lambda. That one actually, it looks more complicated if you look at the expression here. One second. Okay. It looks more complicated, but if you expand these things around n, when n is small, what happens is for the noise estimation, you never even ideally, you never get Heisenberg scaling. This thing at most scales linearly with n. So this formula seems a little bit complicated, but if you expand, it goes like n over lambda, basically. So it still has a peak, but even at its best, it starts linear. So to estimate unitary model parameters, you can get Heisenberg scaling, but you can lose it in the presence of noise. To estimate noisy parameters, typically you don't even get it in ideal conditions. But this is an example in which you can estimate both parameters at the same time. And you can use this information to optimize your implementation. I don't know how the same model works if you start from an entangled case. So if you use these n rounds in parallel now, start with your GSZ case, see what happens there. I don't know. So it can be that some schemes are more robust than others to certain types of noise. It can be an interesting exercise to complete this particular example and also to look at what happens in the other situation. And on the other hand, a whole new frontier of working on these problems is not just passively being affected by the noise, but introduce some active controls. So how would they look like? Oops, sorry. Well, there's a whole hierarchy of schemes, if you like. So quantum error correction, or if you want control in metrology. For a scheme like this, what would you do? So you have, first of all, you can use ancillas, which are supposed to be clean. So we mix up things a little bit. So you have your state, you have an ancilla. On your system, you implement the unitary and the noise. That's unavoidable. And then you have an ancilla which is not affected. So you can introduce some operation here. Then again, your channel with unitary and the noise. Another operation here. And you can repeat this many times, and eventually you measure. So this one is the control. And this was, let's say, the unitary and the noise, the unitary and the noise. These kind of schemes are very general, but now it's a whole lot of extra complication. What is the ideal thing here? Basically, the intuition of your friend from the break, where I was asking, can we take this noisy channel and kind of basically invert it? What we want to do here, we want some operation that keeps the signal but cancels out the noise. It's not going to be perfect. Sometimes you can, sometimes you cannot. For instance, if you are estimating rotations around Z and you are having dephasing in the Z direction, even with the most sophisticated control, you are not going to recover the Heisenberg scaling. But in principle, now here, this is a hybrid scheme. You start from an entangled state of your signal and an ancilla, so that basically the ancilla keeps some information about your system, and you use this information in a way to reinject the purity of the signal in here. So how to find this? There's very efficient ways of doing it numerically. So the guy from which I was copying the proof, Rafał Demkowicz-Dobzhansky, he has several papers in which effectively constructs a computational framework for optimizing actively controlled scenarios for estimation and maximizing quantum Fisher information and the geometry of your networks in various situations. I think it's a very interesting problem. Of course, if you care about other factors, including cost of implementing all these gates, then the whole problem changes. Yeah. So if you have your figure of merit, which is only maximize the precision at all costs, then fine. You can construct some protocol that's maybe super expensive, but gives you close to the best. On the other hand, if you need to keep yourself under limited resources, then you change the parameters of this optimization, and then it becomes maybe a more complicated problem. All of these areas are very much active, and I think there's a lot to do, which might be or might not be tailored to specific problems that people have in mind. Yeah. So bringing these tools to other areas is what we really want to do. So some of these are very mathematical. I'm in the School of Mathematical Sciences. Some of this is purely mathematical. They interface statistics with linear algebra and basic information theory. But ideally, then we will soon reach a situation in which these methods will really inform how sensors are built and how can we actually establish new standards for quantum technologies. So I think we are getting close to finishing, and I want to leave time for questions. I just want to mention another scenario which is very much equivalent to what we have said so far. So far, we were talking about qubits, okay? And our resources was the number of this n, which can be either the number of qubits in an entangled scheme or the number of repetitions in a parallel scheme in sequence. You can have a very similar situation if you just think about, say, Mach-Zehnder interferometer, when you want to estimate phase. We were doing phase in the qubit case, and that phase was very much like a magnetic field. Here you can talk about optical phase, where effectively you have now continuous variable systems, so modes of a field, and you have one beam splitter here and an input that you typically don't control, can be the vacuum. What you control is is the input in here. This will be like the analogous of the initial state we prepare. Yeah. And actually what we care about is that we have some correlations at this stage. So you can either think of having some state that is non-classical in the input here, and the other arm remains the vacuum. Or you can directly think about creating an entangled state between these two arms. These two scenarios are very much similar. Like before, we're talking about coherence versus entanglement. Here, you can talk about, for instance, squeezing here versus entanglement at this stage, and they are equivalent again in ideal situation. Where squeezing means that you have quantum states which are still of minimum uncertainty in the product of position and momentum operators, or if you want intensity and phase quadrature operators, but you reduce the variance on one, and as a consequence, the other one increases. So you are really squeezing out this ball into an ellipse where you minimize the noise on one quadrature and you dump everything on the other quadrature. And the goal of these kind of schemes, which were probably one of the very first type of schemes to be studied in the context of quantum metrology, we're talking about, say, Carl Caves and others from maybe 40 years ago, about the time I was born, 40 and more. The goal is you really want to estimate phase differences, actual phase. So of course, the light or whatever waves that are traveling across these arms of the interferometer, if there is something which is creating an imbalance, they travel slightly different distances, and there is overall a relative phase between these two. And we want to detect this relative phase. So that's why it says here, the sample is the phase. So our parameter theta is the phase difference between the two arms of the interferometer, and we want to measure at the end. Exactly the same problem. The qubit was like a quantum information circuit model for something like this, but that's the OG, the original problem. Why it's the original problem? Because people have looked into this for decades for the most important application, LIGO, right? So LIGO is literally a massive interferometer. And why we took so long to see the gravitational waves was because even when they start from catastrophic events like these black hole mergers, by the fact that the gravity is so weak, so they carry a signal which is on a scale that we don't really imagine with our instruments, right? So we need interferometers that are able to be sensitive to phase differences of the order of 10 to minus 30 and less in whatever units they have. So eventually they did it. And they actually did it in the first, the Nobel Prize winning papers and so on. They did it without using any additional quantum resource in the input. They were just really, really highly sensitive interferometers here, and the measurements were really precise. But if you play, so effectively the first LIGO detections, they were standard quantum limit. Standard quantum limit in this context, it means at the input here of this A in, you have just optical coherent states, like states of a laser pointer. And these states, they have a certain number of photons. And your resource, if you calculate quantum Fisher information for phase estimation in this problem, you, with an input that is made of optical coherent states, you will just find quantum Fisher information proportional to the mean number of photons. So there's n again, it just means something different. Instead of number of boxes for the qubit model, this will be mean number of photons. So standard quantum limit n, of course, if you have some prefactor that is large enough, you can amplify this signal anyway. And that's what they did, and they detected it. But there's room for improvement, and I think in the past 10 years, they've been working to upgrade LIGO to the advanced LIGO, which can detect even fainter signals because it now exploits non-classical resources in the inputs, like squeezing, which lets you achieve a quantum Fisher information idealized that scales like n squared again, where now n is again mean number of photons in this squeezed beam. So this, I think, is a plot that was in a Nature paper about 10 years ago. So far, the LIGO. So I think now they've been already advanced LIGO detection, but when they started seeing stuff, LIGO was pretty much at the standard quantum limit. That was the red line. And theoretical calculations show that you can still increase the sensitivity. And look at the orders of magnitude here. We're talking about 10 to the minus 22, 10 to the minus 23. But you want to just do the little bit more, no? With an experiment of that size. So you can still beat the shot noise. Standard quantum limit is the same thing. So you can beat the shot noise limit by using some squeeze states and further reduce basically the intensity of the signals that you can pick up. Okay, so if you want, this sensitivity is effectively the resolution of your instrument, yeah, the thing that you want to minimize. And it would, and how far down you can go would depend on the quantum Fisher information of the problem. So the standard quantum limit is this thing which goes like n is the dashed line which they've reached. You can go further down with squeezing, and then there should be another line at some point just telling you can't really bring it down to zero because quantum mechanics still limits you, but you get a better scaling, which, given the magnitude of those signals, still plays an important factor. So we're going to see more and more developments in this field and others by trying to get as close as possible to the ultimate limits. And I think in the rest of this school, you're going to see applications of this whole mathematical formalism to a simple problem of imaging. So optimize the reconstruction of images from telescopes or from microscopes, or resolving stars that are very close to each other with respect to the wavelength of light. And that's a problem that seemed basically impossible until maybe 10, 15 years ago, when it was realized that you just need to do better measurement because this framework tells you that they exist and you can actually implement them. So you'll see more of this from my colleagues the rest of the school, but I think at this point I will close. So what did we learn today? I hope I went through this. Yeah, so I started from discriminating between quantum states, introducing some measures of distinguishability. Trace distance is related to optimal probability of distinguishing two states. Bure's distance is related to quantum fidelity, which we have then recovered later as a geometric interpretation of the quantum Fisher information. So we recapped what you have learned today about statistical interpretations of estimating parameters. And you can always extract probability distributions from quantum states, but you have an extra freedom because it depends on what you measure. So the whole business of quantum information, quantum estimation theory is about, on one end, maximizing the information you can extract from your states by optimizing over all the measurements and finding most sensitive probability distribution. This leads to the quantum Fisher information and the quantum Cramer-Rao bound, both for single and multi-parameter estimation cases. On the other hand, you also have the freedom of exploiting quantum effects from the beginning in preparing your probes to make advantage of phenomena like coherence, entanglement, squeezing, which lets you beat the limits that you would normally have if you don't exploit those phenomena. And this leads to Heisenberg versus shot noise limit. We have seen ideally Heisenberg limit is there to be reached, but as soon as you have some noise effects, you can lose it. And you can still try and control your setup in order to counteract that noise. But to do so, you need to know it. So you need to be able to estimate signal and noise, like in the example that we have said. And I briefly brushed over applications to optical interferometry, like in LIGO. And thank you very much for all the questions that were very good. If you have more, let me know. And otherwise, we can talk at any time. Thank you.
Thank you very much, Gerardo. So let's call. I believe we have an incredible lecture. Students here are excited, I see. And okay, we have time for questions, maybe. In the audience, Anton, what about online?
From no more question, at least right now. Oh, yeah, there is a
They
question
appear
actually right
just
now.
now.
Yeah.
Yeah,
Any
so thank you.
papers? Yeah.
Yeah, so of course I put here just two which are kind of tutorial styles. Papers for further reading, there's a lot. Depends on what exactly. So I touched on several aspects. So I have also a review myself, if you like. So there is one review article on quantum metrology published in Review of Modern Physics. It's called Quantum Enhanced Measurements Without Entanglement. I can mention that one as well. Or if you have some, this is a big topic. So if you want to send me an email, that my email is on the screen now. I can, and you tell me which specific aspect you are interested to go deeper in. I can send you some references specifically. That's okay. I will just put, yeah, I put here.
Is this article by Brown?
Yeah, that one is the one with me actually. Yeah, I should have mentioned my own, but
Gerardo, a little bit technical. I have a little bit technical question. Could you please share your notes today with students?
Oh, I will, of course. I'll send it. I will just generate some
PDF,
some
yeah, you can say. Okay, other questions?
Yeah.
Anton? I see
No
online
more
something
question from
appears.
No, it's me. It was just me. I sent the article in the chat.
Okay. See. Questions? Okay, so I don't see more questions, but we had questions during this lecture. And Gerardo, thank you very much again. This
Thanks
was
so
really
much for
incredible,
inviting me.
really nice. It would be, of course, we would be really happy to see you here in Kyiv in person, not in such a for electronic format. But security issues, you know, that it's now this is not the time, but hopefully next year this will be possible.
I really hope so. I want to come.
Yeah, thank you very much. Thank you very much again. So thank you.
Thank you.
And
Thanks,
have
everybody.
a nice day.
Bye.